Okay, so let me remind you that from the previous video, we have this x of t being the integral from 0 to t of b1 dbs for t greater than or equal to 0. And we know that this equals to, there are two cases. The first case, t between 0 and 1, so it's b1, bt minus t. And then b1, bt minus 1 for t greater than 1. This is 0, this is 1. Look at the case t between 0 and 1, this is b1. It is b1 bt minus t. And we know that for t between 0 and 1, this stochastic process is a near martingale. So over here is a near martingale. Now, how about when t is greater than 1? When t is greater than 1, it's very easy to see that this is a martingale. So you see that effect of this b1 in the integrand. When b1 has effect, namely when t is between 0 and 1, this stochastic process is a martingale. But once t is greater than 1, then b1 is adopted with respect to the filtration of the Brownian motion for t greater than 1. And therefore, for t greater than 1 is within the Ito theory. So this is within Ito theory. And this is the new theory. On the other hand, consider the stochastic process. Which I denote by y sub t. And this is the integral from t to 1 of b1 dbs. And for t between 0 and 1. It is easy to check that y sub t for t between 0 and 1 is a near martingale. And for t greater than 1, a martingale. Okay, let's go to the next page. So this is page 35. Example 2. Consider the stochastic integral from A to B of B1 minus BS dBs. So this time the integrand has no equal part. It has only the counterpart instantly independent. So consider this as stochastic integral. We can easily derive. There are several ways to do it. You can apply the definition, or you can find out the integral from A to B of B1 and the integral from A to B of BS, and then put them together. So in any case, it is easy to find out or to evaluate this new integral. That equals to B1 times BB minus BA minus 1/2 of BB squared minus BA squared, and then minus minus 1/2 of B minus A. So this you can easily derive. Okay? One. Let's put A 0 and B equals to T. And then we have this stochastic plus xt equals 2. In this equality, put A equal to 0, B 0, 0, and then B equal to T. And this is what we get. B1 BT minus T minus 1/2 of BT squared minus T. This is for T between 0 and 1. And now you see here, B1 minus BT, B1 BT minus T. This is a near martingale. And this part here, BT squared minus T, this within Ito theory, this is the martingale. And therefore, X sub T is a near martingale. And 2. Oh, I'm sorry. No, this is not 2. We can compute a value just as before, the value for t greater than 1. And then we get this x of t equals to b1 bt minus t minus 1/2 bt squared minus t. This is for t between 0 and 1. And when t is greater than 1, what do we have? We have b1 bt minus 1. So you see this t remains 1 when t is greater than 1. And the second term is within Ito theory is the same. This. And again, we have a situation like that, 0 to 1. Over here is a near martingale. And over here is a martingale. We go to the next page. This is page 36. And that is a 2. Similarly, we have a stochastic process. Y sub t being the integral from t to 1 of b1 minus bs dbs. And we can compute this in a similar ways, and that equals to 1/2 of b1 squared minus 1 minus b1 bt minus t plus 1/2 of bt squared minus t. And this is for t between 0 and 1. And when t is greater than 1, it becomes 1/2 of b1 squared minus 1 minus b1 bt minus 1, and then plus 1/2 of bt squared minus t. This is for t greater than 1. And now observe, when t is between 0 and 1, the first term is a near martingale. And the second term is also a near martingale. and the third term is a martingale. On the other hand, when t is greater than 1, now the first term here is is adopted this because t is greater than 1. So this is a martingale. And this part, the second term, is also martingale. And the last part here is also a martingale. And so again, we have the same situation. That 0, 1. Over here is linear martingale. And over here, when t is greater than 1, is a martingale. Okay, this is enough for this video. And next time, we will continue to pursue to discover some new property of our new theory of stochastic integration. Okay, bye-bye.